Hey everybody, like you said, I'm Thomas, and I want to talk about computer systems that look quite a bit different from everything we've seen so far this week. So we've looked at web servers and data centers and things like that, but there's a lot of concurrent software, and there's a lot of computer science going on in systems that look very, very different. So imagine a car. If you go out and you buy a car right now, it's got anywhere between 15 and 30 CPUs in it. Combined, those CPUs have about 100 million lines of code on it. And it's very difficult to write all those lines. The software engineering alone accounts for 10 to 20% of each cost of each new car. So there's a tremendous amount of engineering that goes into that. And it doesn't always go right. There are terrifying security vulnerabilities in a modern car. People have demonstrated that you can call a car and turn its brakes off. There are security vulnerabilities and bugs in things even scarier than a car, like medical linear accelerators. This is a particularly famous example from the 1980s, where a bug that we're going to look at in this talk led to the radiation overexposure of about 6 or 8 people and the death of 3. We don't actually have to look at complicated systems like cars or medical linear accelerators to see complicated concurrent embedded systems. I've got one right here. It's a switch attached to a computer. And for those of you who don't read schematics, basically it's this. It's a push button and a CPU. And what I want to have happen is I want the CPU to know when I've pushed this button, and for it to be able to count how many times I've clicked the button. The problem is if we look inside this switch, and in fact if you look inside any switch, it's got a spring in it. And that spring means that when I push a switch, it actually bounces up and down a little bit. So it clicks too many times. And so if you were to hook an oscilloscope up to a switch and turn it on and off, it looks something like this. This is called switch bouncing. And people who do electrical engineering, if you're taking a double E course, this is one of the first things they teach you how to do. So you go onto the internet and you Google switch debouncing, and you find an algorithm that looks something like this. It says, wait for the user to push the button, then wait for the button to stop bouncing, then read it. So this is relatively simple, and everyone who's ever programmed a microcontroller has written this block of code. The problem is I have this microcontroller because I want to do something with this chip, more than just read the button. Let's say I'm doing some math in the background. I somehow have to interleave this math with waiting for button presses and waiting for timers to go off. So this becomes a multi-threaded concurrent software engineering challenge just to debounce a button. We've been studying this kind of software, this kind of low-level microcontroller programming as real computer science at Rice for about 5 years in our research group. We've developed an open source Python interpreter that runs on microcontrollers, devices with about 32K of RAM. And it's open source. You can go download it. There are lots of people at Rice who use it for various classes. We've taught about 100 people how to program on a small robot using this system. It's very easy to get started because it's a nice high-level language. But when you try to do real problems with it, when you try to build real applications, you find that the I/O is hard because of all of this concurrency problem. Python is not a great language for concurrency because it doesn't have any built-in primitives for this sort of thing. And in fact, any imperative programming language like C, that's the primary way that people program these things, it's a terrible way to do this. So we've developed Medusa, which is detailed in great detail in the paper, and it's a variant of Python that adapts the actor model of programming and message passing for managing concurrency on microcontrollers. I'm not going to get into how all of Medusa works because we only have a few minutes here, but I want to look at one particular thing, which is how we deal with I/O in Medusa, and how we can take message passing that we use for software concurrency and that was developed for software concurrency in the actor model, something like that's how we do concurrency in Scala and Erlang, and how we can adapt it to do I/O on microcontrollers. So why is this such a difficult problem? Well, the current techniques that people use in imperative programming languages are really inadequate for dealing with concurrent I/O. So the simplest thing, and the thing everybody does like on Arduinos, is to pull a device. It's simple, it's easy to wrap your head around, but it's very slow. Generally, when people are building production products, they write hard-coded interrupt handlers. And that's faster, but people screw it up. So we're introducing a third technique we call bridging that basically gives you the advantages of both. So let's look at a polling implementation of this button debouncing. I sit, I read the button repeatedly, I wait for it to go down, then I set a timer, then I wait for the timer to go off, reading over and over and over again, and finally I read the value of the button. So these are two threads that are running in parallel. The problem with this is these two sections in red here, where I'm just spinning around some condition. Most of the time, I'm spending in there, in that loop. So I'm wasting a tremendous amount of CPU cycles just reading the same value over and over again from an I/O port. This becomes a pretty big problem, and it's catastrophic in practice. We've tried to build applications with our Python interpreter using polling techniques, and it doesn't work after you have about 5,000 events per second. Maybe that's not too fast on this sort of button. Maybe you could do this if you had this sort of button. But if you had a sonar device, let's say this rangefinder, 5,000 events per second, that happens relatively frequently because I'm getting data, not just button presses, I'm getting actual bytes from this thing. So by the time I pass 5,000 bytes per second, I'm screwed. So alternatively, I could take out those spin weights and replace them with interrupts. So now the hardware comes and wakes me up when I'm ready for this. And this is conceptually simple, right? You can look at this and you can say, all right, well, when the button's expired, run this code. And this is what vendors tell you to do. If you read the TI documentation for the microcontrollers that we use, they say, write all this stuff in interrupt handlers and it'll be fine. The problem is what I've written here isn't complete. There's a whole lot of shared state and lock manipulation that I need to do to make this right. Just to do button debouncing, I need 170 lines of C. It took me a couple of days to get this to work on a product where I don't have a console, I don't have a debugger, all sorts of things that I'd really want to debug multi-threaded C. So this is actually really hard to get right. And it's this exact scenario that's led to a lot of bugs in practice, like the security vulnerabilities I talked about in cars, and the overdoses that happened from the linear accelerator in the 80s. Moreover, we're using a bytecode interpreter where this is really hard. I can't just interrupt things. So if I'm executing one bytecode after another, and I get a button press, now I want to fault into some interrupt handler that I want to write in the high-level language. If I just start executing bytecodes from the other stream, I need to be able to go back and execute my first thread. So now I need to write a reentrant interpreter. That's going to be hard. Alternatively, I could wait to complete a bytecode, and then go ahead and run my delayed interrupt handler, but I might end up missing a lot of events. So What we do is we take these external hardware events and we turn them into software messages. So because we're using an actor-based programming language that looks a lot like Scala or Erlang, all of the software threads are synchronized with message passing. So let's just turn those external events into software messages and send them to the people who are interested in them. So a particular thread that might be interested in when a timer expires or when a button is pressed will say to the virtual machine, I need this data. Then the event happens and the virtual machine turns that event into a software message. This is similar to what microkernels did with interrupts, but it works in a slightly different way, and I'll show you that in just a second. So let's say we're going along here and we're executing bytecodes. We're doing the background math that we're trying to do for our little microcontroller application. I add some data, I call a function, I'm going to call another function, but all of a sudden I get a button press. And instead of switching execution to a whole different thread, I stop and I execute a very short interrupt service routine that just takes this data, that just takes a record that the event has happened, and copies it into a fixed size buffer. So right here, I'm showing the entire C interrupt handler to take an I/O event, a button press, and turn it into a software message. I make 3 function calls, 2 down to the hardware to read the event, then 1 to copy it down into this pre-existing fixed size buffer that we call a bridge. This is a very short interrupt handler, and it's almost impossible to screw up. There's no manual copying, there's no locking that a programmer has to do to write this. So as long as you make the right API call here, you can't actually introduce deadlock or concurrency error. This is something that's really easy to do in a much more complex interrupt handler. All right, so now once we finish that interrupt handler, we can go right back to executing bytecodes. And I don't need a reentrant interpreter here because I'm not modifying any of the virtual machine state. I'm not allocating data on a heap. I don't have to do anything like that because it's all in this pre-allocated buffer, this record of the event. Now, once I've finished the current bytecode that I was working on, the one that got interrupted, I can stop and I can actually deliver this data out of the intermediate buffer. So I take this event and I allocate some space on the heap for a new object. I copy the data and I remove it from the buffer. So now I have a place for new data if I get interrupted again. And I can go back executing my original bytecode or the next bytecode in the sequence. So this two-phased bridging is fundamentally different from interrupting a program and switching context completely. I'm stopping very briefly, copying just the data that I need to copy at that exact moment into an intermediate place, completing my current operation, completing the execution of a bytecode, and then I'm copying the data later. This later can really be any time as long as that intermediate buffer doesn't fill up. So we do it at the end of the next bytecode. In a different system, this could be implemented differently. But the key is that I do the actual allocation of a message and the actual copying later at a time where I don't need to make my code reentrant. This makes programming a whole lot easier. So whereas when I used interrupts, I needed a very complicated interrupt service routine that manipulated locks, allocated data, copied things around, and when I used polling and polled the I/O device a whole lot, I had terrible performance because I was checking the same I/O port over and over and over again. I can kind of get the benefits of both by using message passing and using bridges here to automatically turn a hardware event into a software message. if you look at the code, and we have lots of code examples in the paper, the implementations of user code that use message passing, they're structured almost identically to programs that use polling. And you just sort of get the performance of a non-blocking implementation for free. So, in general, a surprising number of computer systems, and basically all embedded systems, are concurrent. Whether they have one switch and there's the world's simplest embedded application like this, or we make it really complicated and have 2 switches. Current applications, current runtime systems, things like the Arduino, things like our previous work that we described 2 years ago, our Python interpreter, they're inadequate. They don't solve this problem. The actor model, which is a great model for software concurrency, turns out to be a great model for hardware concurrency also. It lets you program the device as if it's a blocking system using polling, but you get performance like you do if you use hard-coded interrupts. With that, I'll take any questions.
Lev Istrovich, T-Show Research. Thank you for a great presentation.
Thanks.
It was very clear. I have a question as to why you chose to use actor model and Scala when, so similar approaches have been done in the Linux kernel with delayed interrupt handlers
Sure.
and bottom half handlers, etc. So you could generally implement this sort of stuff with, let's say, a Python thread and an
Sure.
event, as long as you have a little C routine to handle the interrupts just like you're doing and putting them in a bridge or in an event queue or something like that. But so I was just wondering what is the advantage of using Scala and the actor model?
So the main reason why we're using the actor model instead of using a multi-threaded shared data model is because there's a lot of detail in the literature that says that synchronization to shared data is something that people get wrong. And it's very complicated to get right. There's lots of papers for data race detection and things like that. And in a really critical application like an embedded system, like a controller for the anti-lock brakes, using a programming model that eliminates the possibility of having deadlock is much better than one where you have to code around it. So the entire design of the system is based around using message passing for software synchronization. So extending that to synchronize with hardware makes programming a whole lot easier.
Okay. Thanks.
Hi. Yeah, I was a bit confused about how does it work. So whenever there is this interruption, you basically create an event.
Yes.
Then by the time that the current process has finished its job, then you pick the event and you deliver the data.
Yes.
So I was wondering, is it possible that that process lasts a lot of time, and then basically you starve the events that are potentially being appended to that bridge buffer?
Sure. So the question is, what happens if later, delivering the message later happens too late, and I fill up this fixed size buffer?
Yeah.
So yes, that's a problem. These buffers I can allocate at I allocate them at runtime. I can tune the size of them, and that's just a trade-off. This is a fixed memory device, right? I only have so much space on the device. I have to tune this stuff ahead of time. I need to size these buffers so that they don't fill up.
Right.
But if I do, I can detect that I've done it and throw an exception that I then have to fix by probably fixing the device, right, and making the buffer bigger.
Okay, thank you.
Sure.
Daniel Lohmann, Friedrich Alexander University, Erlangen.
Hi.
So is your system capable for hard real-time systems?
So
is
no.
the user interpreter bounded in everything?
No, it's not. And that's
So what kind of embedded systems do you really think you could use for it?
so most real-time systems, they're not hard real-time systems. Hard real-time systems are the anti-lock brakes on your car. A thermostat is not a hard real-time system. It's a soft real-time system. And the delays don't necessarily cause the thing to break, right? So the bytecode interpreter, it's not formally proven. I can't tell you it takes this many microseconds to run an operation. What I can do is I can tell you that it's fast enough, and I can use this in applications where I don't need those where I don't need those guarantees. Now, nothing about what I've shown here today, nothing about using software messages to synchronize with hardware, that's not necessarily tied to our particular bytecode interpreter. And so you could build this sort of thing for a machine that did support hard real-time guarantees.
And do you support any 8-bit platforms?
Not at this time. Again, just for implementation reasons.